very quickly. In terms of the grades, you are seeing your midterm grades. And if you're wondering how the grades were computed, basically it's very hard to compute the overall grade just based on the first assignment and the midterm. Because people generally do well on the assignment and not so well on the midterm, which is understandable, it's unpredictable. So the way we've calculated the grades is that 75% goes for assignment 1, 25% goes for the midterm, because midterm is going to be 25% of your final grade, right? So it's however you want to judge it, right? It's very hard to predict what your final grade will be based on your midterm grade. But nonetheless, in terms of the distribution of the grades, a number of people aced the first assignment and the midterm. So there's a number of people who are actually getting A pluses. And there's a lot of people getting A's so far based on your midterm and your assignment 1. And then there are, some fraction of people getting B's and B minuses, and very small fraction of people are getting C's and such, right? Primarily those people who didn't do well on both the assignment, first assignment, and the midterm. Okay. Ultimately, a lot of people are asking, are we going to be curving? I don't want to do curving right now. I will do, if necessary, we will do curving at the end of the class, right? But so far, a lot of people, I would say more than 50%, are basically getting an A in the class as a midterm grade. Okay? Let's quickly look at the midterm. And kind of like, if you look at it from the hindsight, and I think we'll post the solutions at some point. Can you guys see? First question, write down the Gaussian, the log likelihood. Here's the probability, take the log, it's this thing here. Okay? Common mistakes, people forgot to put n's somewhere, or forgot to put squares and so forth. So take derivative of the log likelihood with respect to the mean, set them to 0, you get the maximum likelihood estimation, right? Take the derivative of the log likelihood with respect to the variance, a little bit of math, you get the variance. Okay, so nothing like, hopefully if you just look at the book, it's pretty trivial. Find that the expected value of the maximum likelihood is unbiased estimator. It's what you needed to show. Just write down the expectation of the average. Push the expectation inside, because these are ID samples. What's the expectation of each one of those data points? By definition, it's coming from the normal distribution, it's just mu. You get mu. Some common mistakes, people were saying, well, you can do it by central limit theorem. Some people were invoking a whole bunch of different things. So this is trivial, right? Any questions? Simple. This particular, the second problem, exponential family, just as a reminder, you needed to show this expression here. In class, right, if you actually look at your lecture notes on exponential family, we've kind of shown this piece, right? You take the gradient, you say, well, this thing has to sum up to 1, right? Take the derivatives, you have this expression. But then you had to conclude that the maximum likelihood estimation actually equals to that, right? Quantity. So people sometimes just wrote this expression or wrote this expression and that's enough. You actually had to, say that that's the stable point of the maximum likelihood estimation. Or even easier, just write down the log probability within the exponential family models. You have this expression. Take the derivative with respect to eta, natural parameters, and it's just you get out the actual solution. Just, you had the expression, take the log, take the derivative, set it to 0, you get the solution. Fairly straightforward as well. Okay? This question I thought was very easy, but there was a lot of confusion for some reason. So let me go through, if you remember this question. So, you have two-dimensional input representing the score of the first and the second assignment, and they want to predict whether you will get a pass or fail in the midterm using a neural network with single hidden layer with 4 hidden units. So now you have this representation. So the question is, what are the values of G, D, and K as the output? The answer is your D is 2, two-dimensional input, the J is 4 hidden units, and the output, you're trying to predict whether you're going to pass or fail. So that's where a lot of confusion came from. Properly, if you want to define it in the easiest way, you only have one output unit, which is a sigmoid, right? And the sigmoid unit only predicts the probability of pass, because the probability of fail is 1 minus sigmoid. You have to sum up to 1. Some people were drawing two nodes here, saying, well, one is for pass, one is for fail. Fine, you can do the softmax if you really want to do that. But then, in the next question, what function should be using for G? And if you have one output, then you should be using sigmoid, right? To predict the probability. So some people said, well, I have two outputs, one for pass, one for fail. But then on this question, a lot of people were asking, well, both of them are sigmoids, right? So now what does that mean? You know, you're predicting probability for one for pass, and you're predicting probability for fail, but they don't have to sum up to 1, right? So that's where the confusion were coming from. People would draw two things and then said, well, each one of them should be sigmoid. If you draw two things and you said it's a softmax, so they have to sum up to 1, then that's a valid answer, right? So that's fine, as long as you had the justification. Some people also said, well, this nonlinearity is just going to be some threshold function. If it's above 0, it's pass. If it's below 0, it's fail. But then if you look at the next question, what function, loss function you should be using, the obvious answer is cross entropy, right? And that's because hopefully on your assignment, you were solving the exact same problem. So some people were confused as to, you know, what should be using thresholding function. And then if you look at, you know, the last question, how do you take derivative of whatever function you came up with respect to the parameters? If it's a thresholding function, you can't take derivatives. So hopefully, you know, and then people were saying, well, maybe it's something else. So there was a lot of inconsistency in the questions where people would answer it one way, but then the following question would do something else and so forth. So some people were losing points on that. Cross-entropy loss. Some people didn't really have a good justification. Why would you want to use cross-entropy loss? Some people wrote the cross-entropy loss but forgot the second term, right? So people just wrote, well, this is your cross-entropy loss. So just in many cases, I think there are a number of examples where people didn't quite have this question right, which I actually thought was a pretty easy question. Computing the derivatives, you just compute the derivatives. If it's a sigmoid and so forth, then you get the answer here. If you don't have this sum, that's fine. It's not necessary. If you do have the sum, that's okay, because you're typically summing over a number of training examples, but that's okay if you didn't. Ultimately, what the expectations were is you should come with this representation, right? What is this representation? It's your target minus what your prediction is multiplied by the hidden units, Hj, which is the derivative with respect to the output, sigmoid output layer. Okay? Any questions? Fairly straightforward, right? Let me just check what the confusions were, because TASK, here's some of the confusion. So here you're using either neural net with one output, but you softmax in 3B. So some people would say, well, you have logistic at the output. Next time, you just say, well, it's a softmax over two options, right? So there was a little bit of inconsistency on neural net with two outputs, but sigmoids, as I mentioned, few people applied step function of the output. You can use Bracro, like some people would say, like, just use ReLU at the output, which wasn't making much sense either, right? Choose cross-entropy, but why it's good for classification. Many students forgot the probability of class 0 in cross-entropy and just forgot this term here. Some students actually were using mean squared error as the output. And I guess you could argue that you can use mean squared error somehow to predict whether somebody's passing or failing. But it's very hard to justify. Why would you use mean squared output, right? This is really a classification problem. And your homework one, you really did the classification problem. Few people choose to use custom-made loss functions that are not a function of the output, but only consider classified correctly or wrong. So these are like step functions. They were not differentiable with respect to the parameters and such. Okay? So these are the common mistakes. Now, the next question, this question, I think this, in my view, was the hardest question, probably, right? So here you had to think about what's going on. You remember this question? you have a neural network, you have the sum of squared error function, and now you say, suppose that the Gaussian noise with zero mean and variance sigma is added independently to each of the hidden variables. Now think about what that means. That basically means in a neural network, given some input, you compute the hidden variables, and you just add Gaussian noise to the hidden variables, and then you proceed to the output in the prediction. Right? So you're just corrupting HJs here with Gaussian noise. And the goal was to show that what this does is you can write this down as a sum of the squared error for the noise-free H's with an addition of the weight decay regularization term, with addition of L2 regularization term, right? So it's interesting what this question is asking you, if you think about this, is that in this particular neural network, if you take the first hidden layer, you add Gaussian noise, and then you do a prediction, which is just your mean squared error, your error for predicting real valued output, and you look at the mean squared error, it's the same as having your original model, but with L2 regularization on the output weights. Right? And if you think about this kind of a lot of people were using this idea, trying to say, well, actually, if I start adding Gaussian noise to my hidden variables in all the layers, then maybe it can make my network, behave more robustly because it's a form of regularization. And it actually works surprisingly well. You can't prove it that it's L2 regularization, some other weird regularization, because you have to go through nonlinearities. But this question kind of gives you a little bit of justification, right? That adding Gaussian noise to the hidden variables is a form of regularization, right? So let's look at how you do that. Here's the first thing that you needed to figure out how to write. And unfortunately, a number of people couldn't figure this step out. So let's look at this step. You're basically saying, here's my new prediction, which is going to be given by, I take my HJs and I add some Gaussian noise to it, right? Because that's exactly what I'm doing. And what I can do is I can write this whole thing as Y, which is my original prediction, because I can just look at this and then look at this, plus WJ, the second layer, times epsilon I, where epsilon I is normal zero variance sigma, right? So this is the step that if you've gotten to that step, you could solve the problem pretty easily, right? You are basically saying my new prediction is really my noise-free prediction plus this term here, which is the corruption. And now you can say, well, now what's my error? Well, this is my L2 error, right? I can write it this way. I open up the parentheses, so you're just opening up what this squared is and what this is, and you can just write this whole thing down and take an expectation. If you take an expectation of this whole thing, you will figure out that the expectation of this guy squared is just this term. And if you write the whole thing down, it comes down to this expression. Okay? It really is. There is nothing, once you get to this stage and say your corrupted prediction is the same as the clean prediction, plus this is the corruption, where epsilon is zero mean variance sigma, and you look at the squared, you know what this is. It's this thing, and you know what y is. Y is W0 plus this term here. Just open the parentheses, compute expectations. A lot of things will cancel out. Like, for example, this term will cancel out because the expected value of epsilon is 0. This is where the variance comes in. This term cancels out because its expected value of epsilon is 0. And so now this term is equals to this, and then you just plug in and you get this expression. In fact, you can show that using similar technique, you can show that in linear regression, if you do dropouts on the input space, it's also equivalent to doing L2 regularization and expectation. Or if you, in this case, if you're adding noise to the hidden units, if your prediction is L2 prediction or real valued prediction, if you're adding Gaussian noise, it's again equivalent to just solving the original problem that you're trying to solve, plus this term here. So the sigma here acts as a regularizer, which intuitively should make sense, because if you add a lot of noise, you're really doing regularization, a lot of regularization. right? So that was probably the hardest question on the exam. And then let's see, batch normalization. Okay, so here's what the confusion was about batch normalization. A lot of people got this question right because nothing difficult about it. You know, the only trick here is the following. And if you've gotten this trick, you would get full grades, which is whenever you're doing batch normalization, you're doing batch normalization for the total input before the activation, right? Let's think about this. If I have some hidden unit J here, right, and this is my input, right, where do I do my batch normalization? I do my batch normalization by taking this input multiplied by the weights, and I want this quantity to be 0 mean variance 1, right? If I take these inputs and somehow do batch normalization on them, each one of them is going to be 0 mean variance 1. But when I multiply by the weights, if my weights are large or small, then the total input to the HJ could be something else. So you always do batch normalization to pre-activation. So every hidden unit, the input to the hidden unit is 0 mean variance 1. So some people said, well, you know what, I'm just going to do batch normalization on HJs. So I'm going to batch normalize these HJs. Right. Well, fine, you can normalize these ones, but then you multiply by these W's and it can skew the whole thing, right? It's not going to help you that much. It's important to do batch normalization for the pre-activation. So the total input has to be batch normalized when it goes to the hidden unit, right? Because then otherwise your hidden unit can saturate, right? So there was a lot of confusion as to where to apply the batch norm. There's two options here. You can either apply batch normalization as a total input to the hidden, or you can also apply batch normalization as a total input to the output. That's fine as well. Even though in many cases people don't really do that. People do it batch normalization as a total input to the hidden states, hidden units. And so as long as you've written kind of these expressions, you would have gotten the grade, or you've gotten the marks. And then you're kind of like saying, and such. And then you pass it through nonlinearity. Now, people were asking, how do we need to use mini batches for batch normalization? Why do we need mini batches for batch normalization? As long as you can say, many cases, you need to use mini batches against to compute mean and variance. Right? You can't really use one example. There's no mean and variance. So that's why people are working with mini batches. So as long as you give a simple sentence like this, they should be fine. And then the question is, how would backpropagation be modified? Briefly describe the steps. As long as you said that we need to differentiate the way modification, we need to differentiate with respect to the means and the variances, right? When we do batch normalization. Some people said, well, we're going to be applying it to the batch normalization layer, but not really specifying exactly the steps. You would get partial credits. Okay, you didn't have to write down the definition, the derivations, and such. You just had to write down that the way it has to be modified is you really need to take into account the derivatives with respect to the means and the variances that you're computing, right? These quantities. So let me see if I've missed anything. I've written down. Yeah, students forgot writing is like the first step. Some people couldn't derive the last step. They would show that this is for the previous problem, is the regularization term. Question 5, wrong layer for batch normalization. Some directly on the raw input, wrong equations for variance. Some people didn't quite get the variance right. Didn't get equations for the feature shift and scale. This is kind of, once you do batch normalization, you have to multiply it by alpha and add beta to it. Some people forgot that. Many students simply wrote gradients have to be backpropagated through the batch norm layer without explicitly talking about derivatives or any sort of what is it that you needed to do. So you've got partial credit for that. Any questions? Yes?
When you batch normalize, is that always just for the input layer, or can you batch normalize each layer?
No, the idea of batch normalization is that you want to batch normalize every layer. So if you have 10 hidden layers, you batch normalize every single hidden layer. So you batch normalize whatever goes into the hidden layer, right? Pre-activation within the hidden layer. So the whole network stays normalized. And so when you're doing backpropagation, it's always in the right part of the regime. You never get these big saturations. So that's actually, batch normalization actually has become one of the kind of standard techniques. You can't really train a lot of networks without using batch normalization. Yeah, question?
Can we add a noise to the hidden layer so that even equivalently we add a L1 to the relation to the
So just quickly go to this. So the thing about this particular problem is the reason why we could do this expression is because the output was a real valued output and our loss was squared loss, right? If you do it at like, to the sigmoid output, that's not going to work, right? Because if you add Gaussian noise, passing the Gaussian noise to this nonlinearity doesn't mean that you get a Gaussian noise out. You get something out other than that. So then the proof breaks down. You can't really do that. So if you add Gaussian noise to some hidden layer 3 and then pass it through multiple nonlinearities, you can't really derive anything like that. You can't really say, well, it's like some kind of L1 or L0 or it's going to be some form of regularization, but there is no explicit form for it. But this is just a motivation that if your output is linear and you add Gaussian noise to the hidden variables, in expectation, it's just like doing L2 regularization, which is nice. And that kind of motivated a lot of people to think about, what if we just start adding Gaussian noise or other forms of noise to like make our networks be more robust, and that is some form of regularization. Okay, so back to our previous. Any other questions, by the way? If you look at the midterm, it's actually pretty simple, right? In hindsight, it's actually pretty simple. I was surprised that nobody finished earlier. Like everybody sat for 75 minutes, which is I think that maybe like you have to do a few derivations, but overall there's only this one question that you have to think about, right? The adding noise to the hidden states. Okay, so today we're going to continue looking at sequence-to-sequence models. If we don't finish, we'll finish next time. I've shown you this example of doing visual attention, right? And I think that we finished last time looking at both of these examples. Here's another example of reducing the resolution with a pyramid encoder. And by the way, I should also point out that just so that you have access, a lot of these slides were borrowed from ICML tutorial, sequence-to-sequence ICML tutorial. So I encourage you to look at, I think they have a recording of the whole thing. If you're really interested in these models, they've done, Oriel and Navdeep done a really good job at, from Google to summarize a lot of different things. And I think they also put some code online. So if you are interested in looking at these models, you're more than welcome to look at the code. Okay. So last time we've looked at this particular problem of doing attention when you're doing recognition. Here's another example. Another example of taking the acoustic model and learning to spell. So here they were actually trying to go from speech to spelling each particular character, right? And as I mentioned before, people started applying these kinds of sequence-to-sequence models to a lot of different things. One thing that they've done here is they've looked at the reducing the time resolution, because it's very finely scaled, with a pyramid encoder. So you have a bidirectional STM, and then you're saying, well, these things get combined, these things get combined, and you have bidirectional LSTM, bidirectional recurrent network, and so forth, right? So there's a lot of different architectural choices of stitching things together in different ways. And here's what they've shown. So somebody is saying call AAA roadside assistance, and then from the beam search, from the decoding, they've got call AAA for road assistance, or the second best example, call AAA road assistance. The third one was call trip way road assistance. and call XXX road assistance. So you can see that the log probabilities and the word error rate the log probabilities go down. So obviously you choose the best one. Sometimes, this is also funny, called cheap way assistance, because you can sometimes make a mistake. There was another application area which was pretty cool, lip reading. This is something that people worked on for the last 10 years. And there's like a few papers, LipNet and lip reading sentences in the wild. Is really the idea here is that I show you the video of someone's face, and based on the visual features of your movements of your lips, you're trying to predict what the person is saying. And if you look at, I think that on this website you can find the data set, you can find some code for this project, and they were able to actually achieve some reasonable results. Like they've looked at these BBC channels and number of hours of training, so you can see these are fairly large data sets. So you have about 5,000 hours and about 120,000 sentences that you can train from. Right, because all these videos are transcribed, somebody's saying in sentence, and then you have the corresponding text. You don't have corresponding alignment for every utterance and what this utterance is, but you have the alignment of a person speaking, and then you know what the person is saying. So you're trying to basically build the model, and this is what the model looks like, which is, let's see. So the model looks like you have you sort of have both the sequences of videos, and you're processing them using convolutional networks. You have a sequence of what the person is saying, and I guess you're trying to predict in this kind of using attention of what the person is saying and what the person is lips look like. You're trying to predict what the person, I guess, will say or is saying. So these are, this is actually pretty recent. This is CVPR 2017. I think they've used this for finding a good embedding space, and then they were using sequence-to-sequence models for just taking the input, having the embedding of what the person has said so far to predict what the person is going to be saying next. And it actually works pretty well. Like, it's not, of course, these are conditions that there's a lot of debate. These are very kind of, BBC videos. There's a person sitting, the face is always registered, the person might be moving a little bit, but there is not a lot of noise in the background and such, right? But nonetheless, you can do that. And this is what happens in terms of alignment or in terms of attention. So this is the image frame when the person is saying something, and this is what the person is saying. So they just wanted to show that if a person is saying good afternoon and welcome to the BBC News at 1, then whenever you say BBC, like this piece, you're paying attention to certain frames in the video when the person is saying BBC, right? So it's kind of nice that the model is able, again, just like in everything else we've seen so far, the model is able to align when the person is saying something versus what the images are, or what the lip movements are, which is kind of cool, right? Because you don't really need somebody to go. Like before, people would go in a line. When I say the word BBC, people will say, oh, this is the clip where the person is saying BBC. And then when the person says afternoon, you can say, well, these are the clips where the person is saying afternoons. Here, you don't really have to have that, right? Person is saying, and then you're trying to figure out what frames correspond to when the person is saying. So you can see that it's kind of is aligned pretty well. The last thing that I want to talk about in terms of applications is the neural machine translation system. And again, question?
In the lip reading model, why do they put the NLP just right before predicting the output?
Over here? I think that when they were training the model, they wanted to use both modalities. There are a couple of different variations. I think that here they should really be, maybe that's not quite the right figure, I guess. During training, I think during training, what they were trying to do is they were trying to find the embedding of both images and the sound to just have a good embedding. But at inference time, and also during the training time, you're only relying on the movements of the lips to predict what the person is saying. So I think that this was just done for learning a good embedding space, and then after that, they should really be, I think they were doing sequence to sequence, which is here's your input, and then you're trying to predict what the person is saying without having audio as an input to the system. So this one, the machine translation system, and maybe we can quickly look at what the system does, because these are a lot of MT systems in industry right now, kind of using flavors of this model. So here you have 8 layers of GPUs. Wow, you have some encoder LSTM. So you're processing a lot. You're processing a lot of information, and now you're doing attention over the space of encoded LSTM in order to decode back the original or to translate it back into a new language. So the only difference what we've seen so far when we looked about a simple models like you translate one to another and you're using attention mechanism, what they've done here is they basically said, well, your encoder is this very massive multi-layer system, and your decoder is also like a multi-layer output system, right? So it's much more powerful, it's much more representative. Probably the capacity of the network is much higher here, right? So you have 8 layers of encoders, 8 layers of decoders, but the system is the same way as what we've seen before, right? It's just a softmax over what the output is. Sorry, let me actually turn this down. Okay, now here's the results of MT. So if you look at the overall architecture, right, the attention is helping a lot here. Paying attention to or doing alignment of what the encoder it does versus what you're trying to decode. But again, just done on a massively bigger scale. And these are some results. So if you look at a lot of traditional machine translation systems were based on phrase-based translations, right? And so this was the previous state of the art. And you can see that this neural machine translation system closes the gap between old system and human system quality by improving the quality of translations by about 58 to 87%. Like from Spanish to English, you are pretty much close to the human level performance, right? From English to Chinese, you still have some room to improve. But like from English to Spanish, Spanish to English, French to English, I mean, look at the French to English. You're pretty much on par with the human level translation, which is remarkable. So you are, in many cases, you are closing the gap. There's still some gap to close from English to Chinese and Chinese to English, as you can see. But these languages are very different, right? So will require maybe you need not 8 layers, maybe you need 16 layers, right? And then you can close the gap. Okay, so now, yeah, question?
After this is streamed, these systems run in real time?
Yes, I think that you can. If you look at, I'm sure they're doing some form of optimization to run them in real time. But in principle, you ask a question, it goes to the cloud, and you can run these systems fairly efficiently. Fraction of a second. There's nothing here that's sort of the only computational bottleneck is the output, is the softmax. But there are a few tricks that you can do, right? Because you have to compute this huge distribution of the possible words, and so you can do a lot of tricks to prune the space down. Yeah, question?
How do you judge the quality of it? Like, do you use the quality of English to translation?
The quality, yeah.
So how do you judge the quality for it? Like, is that also based on grammar?
Oh, the quality. So there is something that's called Blue Score. There are a bunch of different metrics that you can do. It's very hard to evaluate the exact quality of translation systems. There are some proxies to evaluating it. Something that's called blue score. There's a whole bunch of different metrics that you can do because you know what the ground truth is, and then you're trying to kind of like look at how close to the ground truth your translated sentence is. And I guess here they've also done evaluations with human translators, and you can see that it's pretty reasonable.
Does it take grammar into account?
Oh yeah, absolutely. Well, in this case, I'm not sure. I think they also have a language model to improve things. But there aren't specific grammatical rules that you embed into the system to say, if you see this, then it should have that, right? So you're not explicitly taking grammar into account, I don't think. Okay, so let's look at the loss functions when we're optimizing these systems. So when we look at the sequence-to-sequence learning, there is something that's called, cross-entropy is the most commonly used loss function, or softmax. Particularly if your output is a softmax distribution, much like in classification, you use cross-entropy. There's something that's called schedule sampling that I'll briefly talk about. Expected loss, augmented loss, there are different variations on what is it that you want to optimize. There has also been some work on sequence-to-sequence as a beam search optimization. So the people are trying to figure out, like, how do I, ultimately I get some output and I'm using beam search to figure out what's the best solution is. Can I actually optimize the beam search itself so that I can just get the best candidate answer? And then you're also trying to learn decoders with different loss functions. So if you're interested, there's a whole bunch of papers that just exploring different loss functions, and I'm going to show you some of them. Okay, cross entropy. So cross entropy, hopefully by now you know what that is. It's a log likelihood chain rule, just basically predicting the next step given the previous step, the next word given the previous words. And essentially, if you think about this, then you can think of it as a supervised classification for each time step, right? Because at any point in time step, if I'm trying to predict what's the next word, given the sequence of previous words, then I know what my target is. So it really becomes more like a supervised learning problem, right? Supervised learning problem for every single time step at training time, because I know what the ground truth is. Now, there is one thing you have to worry about, which is called training and inference mismatch, right? So let's see what we're doing at the training time. At the training time, I have some input, let's say an English sentence, I encode it, and then during decoding, what is it that I do? Well, during decoding, I say, well, put the ground true what the word was in my translation, and then try to predict the next word, right? But I usually put the ground truth. And then as I'm decoding, again, I put the ground truth, and I'm trying to predict what the next word should be, right? Because think of it a language model. I'm trying to predict what's the probability of the next word given the previous words. And I know what my previous words are because I have a sentence. That's fine. I can solve this problem. But now at inference time, what is it that you do at inference time or at test time? If I ask you to generate a sentence, you don't know what the ground truth is. So I give you English sentence, you don't have the French translation. So what is it that you do? Well, you predict the first word. And given on prediction of the first word, you put it as an input to the decoder, and then you're trying to predict the next word, right? And so forth. So at training time, you always give it the ground truth. But at the test time, it's whatever your hypothesis is, right? Because you don't know what the ground truth translation is. So this is something that's was called you have this mismatch. And that can be very bad. And the reason why is because if your hypothesis is wrong or slightly deviates, it's very hard to recover in the future, right? Because you're not training the model that way. You're training the model by always giving it what's the true translation, trying to predict the next word in the translation. So you're always correcting yourself during the training time. And there was a paper called schedule sampling. What the paper does, the paper is basically saying, instead of giving it the ground truth, actually give it a sampled value from your softmax, right? And still try to predict the correct answer. And then there are a few strategies where people are trying to say, well, start with the ground truth, and then eventually replace the ground truth with the hypothesis. So try to mimic what you do at the test time during your training time. And that particular approach can really help. I think in this case, the sample basically, they also were designing sampling techniques where, with probability 0.9, choose the ground truth. With probability 0.1, choose whatever your best hypothesis is. And as the training proceeds, you're choosing the ground truth less, and you're choosing the hypothesis more. So you're really trying to tell your model, make sure that for this translation, get everything correct. Right? And that can really help if you're interested in kind of the details and how they've done it. This work was done by Sami Benjo. It's scheduled sampling for sequence predictions recurrent neural networks. And they've shown that can really improve the accuracy on a lot of different models, like on machine translation, on parsing models where you're trying to predict parse trees, on speech recognition, and so forth. Like, they really could improve the word error rates and such. So if you are working on sequence-to-sequence model, this is your friend, the paper to look at. Now, the other thing that I wanted to point out quickly is, in many cases, when we look at all of these sequence-to-sequence problems, in many cases, we don't really want to optimize cross-entropy loss, right? Or we don't really want to optimize, specific just for convenience. So, for example, for classification, what we really want to optimize, we really want to optimize 0-1 loss. How many things did I get right? How many things did I get wrong? I don't really care about cross-entropy, right? So what I can do is I can set the rewards. I can start using rewards in my structured prediction problem. And again, these problems are sometimes called structured predictions because you're not just predicting one class, you're predicting the whole sequence, or you're predicting a whole sentence, or you're predicting the whole speech signal. So these are not independent predictions. For example, if you're interested in segmentation, right? People are not interested in cross-entropy, like did I get this pixel right or not? They're really interested in intersection of a union. There's a way of trying to figure out, did I get the box, did I get segmentation correctly or not? For speech recognition, people are interested in edit distance, right? If I'm trying to recognize how many words have I misrecognized. For machine translation, there is something that's called BLEU score, which is again a proxy for human level performance. And we can't really optimize the BLEU score because it's just some score that you're computing. It's not differentiable. You can't really optimize intersection of a union. You can't really optimize 0-1. So everything that we do is we typically set some form of an upper bound and optimize for that. But this is what we're really interested in. And so the question is, can we somehow take this into account? So given a data set of input pairs, x and y, we want to learn some conditional distribution trying to predict y given x that maximizes the expected loss. Okay? So what is this expected loss? This is the expected loss where you sum of your data sets. This is your true prediction, right? Or this is your ground truth. This is what you really want to predict. But then you're taking expectation over your labels y's based on your reward, right? So obviously, if you get the right prediction y, then again, your reward could be how good is your BLEU score, right? So here you're trying to take this into account. And this is something that's hand designed by modelers, right? Because ultimately you really want to see, if I have a translation and I have 10 different translations, if I average over these 10 different translations, I really want my expected reward to be high. I really want all of those possible translations to have high BLEU scores. If one of my translations has like a really bad BLEU score, then your expected loss will suffer, right? This also idea inspired other methods that go beyond maximum likelihood. To give you an example, in some cases people are saying, okay, I have an image. Let's say I classify it as a dog. Okay? So when I train my system, I say, is this a dog? And then let's say I have 1,000 other classes. And if I say, if I correctly classify this image as a dog, then basically this is correct. So you effectively get the reward of 1 for this example. And if I misclassify the dog, I get the reward of 0. So this will turn out to be just a maximum likelihood estimator, right? It's 1 if I got it right, 0 everywhere else, right? That's your softmax. But now imagine that I classify this image as a cat. According to my classification accuracy, it's just as bad as if I classified the dog as a car, right? It's just as bad in terms of the loss function, right? For me, for classification, when you're training, like when you were training your digits classifiers or you're training your ImageNet classifiers, you're really saying, I want this image to say it's a dog. If I say it's a cat, it's equally bad as if I said it's a car, right? So what people are designing alternative where they say, you know what, if I classify it as a cat, there is some penalty here. So I get slightly negative reward. If I classify it as a car, there's a big penalty there, right? Because like this is the mistake that I can't tolerate. And so somehow people would design these new loss functions that kind of shape the overall maximum likelihood estimator. Okay, and we'll come back to that. So in this case, you can sample from the model distribution. Now, these kinds of models are difficult, pretty much impossible to train from scratch. And the reason why is because your Y space, like imagine you're doing translations. This is pretty high dimensional space, right? Imagine all possible sentences you could generate. You can't really go over all possible sentences and pick the best one that have a blue score. That's why people are doing beam search to try to figure out what's the best one. It's more like a greedy algorithm, so you can't really do this. Here's one example, and there is a corresponding paper that basically used something that's called reinforce algorithm. And the reinforce algorithm, what it does is it basically samples from this conditional distribution and looks at the reward. If you sample from this conditional distribution and the reward is really bad, then you basically say it's bad. If you sample from the distribution and the reward is good, you basically say that's reasonable. So what reinforce does, it's like a Monte Carlo estimation. Reinforce basically says, I'm going to approximate the sum by drawing samples from this conditional. So it's a Monte Carlo approximation. It can have high variance, right? Because if you're unlucky and you sample the wrong Y and your reward is really bad, then all of a sudden your gradients will become very large. Right? So you have to take into account, there's a whole bunch of things that you can do to stabilize the gradients. But think of machine translation, right? Just intuitively. Imagine I give you a sentence in English, and then your model produces probabilities of a sentence in French, right? Because you always have the probabilities of predicting the first word, probability of predicting the second word. If you sample from this distribution and you get a really crappy translation, right? Then your model is not good, right? Because it shouldn't be, right? And that's exactly what reinforce is trying to do. Even if you did the beam search and you try the best possible one might look okay, but if you sample from your model and it looks really bad, then you have a bad model. And so this is one example where you're basically saying that you're trying to do more expected loss optimization as training proceeds. So you start with something like a cross-entropy loss, and as your algorithm proceeds, you're going to be sampling from the model and try to optimize for, let's say, a blue score, or try to optimize for 0-1 classification accuracy. So you can look at the paper. It's a fairly recent paper. And they've kind of shown that they can improve on like translation, on image captioning, on different summarization tasks. They can have a fair amount of improvement. Because ultimately, when I measure my image captioning tasks, I measure the performance using blue score. I'm not measuring the performance using maximum likelihood estimation or cross-entropy loss. Same thing for translation, for example. And this also inspired some of the work on something called reward arithmetic maximum likelihood. So here, if you want to find the right output sequence, for example, for speech translation, speech recognition, machine translation, it's kind of like finding a needle in a haystack. It's very risky to shoot only for the true target, right? So think of it when you do maximum likelihood estimation, what does the maximum likelihood estimation says? It says, here's the true target, try to predict the true target. Any deviation from the true target, you're basically considering it as a mistake, right? Which is extremely hard optimization problem, right? Because if you think about translation system that we've seen before, here's a French sentence, here's an English sentence, here's a French sentence. And I'm really trying to predict this exact French sentence. Any deviation from the French sentence, I'm penalizing a lot, right? So the idea here is to expand the targets to make learning easier. For example, by inserting, deleting some random words. So you're almost getting the translation right, but if you missed a few words, that's okay. Same thing goes for classification. Sometimes people are saying, well, if you classify this image as a cat, I'm not going to penalize you that much. I'm going to penalize you a little bit. So I'm going to give you a loss of maybe like minus 0.2. But if you classify it as a car, I'm going to give you a loss of minus 10. That basically means you need to really make sure that you don't misclassify a cat image as a car. But if you misclassify a cat image as a dog, you get less penalty. Yes?
So when you're doing languages, right, and you mentioned French sentence with English sentence, do you want to delete random words or do you want to delete words that are grammatically irrelevant?
You can do all kinds of stuff. The more prior you have.
A name-specific
Sure.
kind of component to this.
Absolutely.
This part of the problem, right?
Yeah.
When you want to kind of see similarity between categories of animals or objects that you're observing, or when you're looking at language, you're basically, you know what you care about. You just need to encode it rigorously into the laws that you described.
That's right. So the design of how do you augment your representation or your targets is totally up to you. The more prior information you have, the better it will be, right? Because you don't have to, you're right, you don't have to remove random words, but you might kind of have a prior of sort of removing irrelevant words or making like, you're producing this sentence, but this other slightly modified sentence is about the same, right? So why would you penalize your model heavily? In some cases, it's almost like, you have a correct translation and you have slightly incorrect translation, but you're penalizing a slightly incorrect translation as if your model is spitting out random sentences, right? So the idea here is to kind of say, can you help the model a little bit by saying, augment your targets with some distribution over possible targets, if you have that prior knowledge. Sometimes you don't. Sometimes you don't have that prior knowledge, in which case your only choice is to predict the correct and ignore everything else. But in many cases you can. So here's reward augmented maximization, where you're basically saying you're going to be solving this particular problem. The details of let me just see. The details of how we do it, you can look at the research paper here. But let me give you an intuition. Here's the intuition of what the model is trying to do. If you set your temperature tau here, so there is a prior that you have to set tau to. You can think of tau as the temperature parameter. So if you set tau to be 0, you're recovering maximum likelihood estimation. Maximum likelihood estimation basically says you're only considering one, your maximum, when you do maximum likelihood estimation, only if you hit the correct one. So think of maximum likelihood estimation, right? You're sort of summing over the probabilities of predicting the correct target, right? And so here, if your tau is 0, you're basically saying, I'm only going to be predicting this thing. Everything else is incorrect, right? But if you start increasing the tau, you can basically say, you know what? I'm trying to predict this because that's the correct answer. But if I'm predicting these pieces, maybe that's okay. And if the tau, more spread out, you can kind of like spread your distribution out. So think of the sentence that you're trying to translate. There is a correct sentence. But if you start, flipping a few words, then you can say, well, assign not just the probability of one to the correct word, but start assigning, the spread out probability. This probability, this sentence has a probability of 0.9, this sentence has a probability of 0.7, so that's okay. We still want to predict those ones as correct ones with probability 0.7, right? So that's a framework that allows you to do that. It's not very trivial to explain it in a couple of slides so you can look at the paper, but there is a way of incorporating prior knowledge in order to try to kind of like optimize this thing. The maximum likelihood estimation basically says predict the correct thing. Here, what you're trying to do, you're trying to say, you know what, your targets can be soft. Your targets doesn't have to be the correct thing, but your target can be a distribution over correct things, right? So you're trying to match the two. And right, and so this kind of works fairly well in some cases. In some cases, it doesn't. Or there is still not, I guess it depends on how you augment, how do you come up with this distribution to say, you know, sometimes just predicting the correct and saying everything else is incorrect is good as well. If you don't have a good pry of how to modify your targets, right? So we've had sort of negative results for this particular problem because maybe I'll just spend a couple of minutes to give you an intuition, is that in ImageNet competition, your goal is to predict correct class, right? And everybody's trying to train the models to predict the correct class. But the real competition is basically telling you that if your prediction is in the top 5 of correct class, if your correct class is in the top 5 predictions, then we still count it as a correct class, right? So if you see an image and your model says it's a car, it's a truck, it's a dog, as long as in the top 5, it would be counted as a correct prediction, right? Because there are a lot of things going on in the images. And so obviously one thing you can do is you can construct ranking-like loss function, which will tell you if you're predicting within the top 5 predictions, why would you want to penalize your model heavily? You really want to penalize your model if your prediction doesn't get, if your correct prediction doesn't get in the top 5, right? Like let's say I'm seeing an image and I say, well, there's a chair and there's a dog, right? The correct class, people labeled it as a dog. But that's fine, right? As long as my second prediction is the dog, I'm still predicting it correctly. And why don't I put my efforts in terms of predicting examples where I can't even get in the top 5 predictions, right? Because these are more important examples to look at. And unfortunately, that doesn't work. For some reason, really trying to predict that this is a dog, and it's not the second choice or the third choice. It really is the first choice. Somehow works better when you do outsample generalization test. So there's sometimes there are positive results, sometimes there are negative results. I think the reason why is because when you train these gigantic nets, they can overfeed data like crazy. So you basically end up saying, you know what, just predict whatever people are predicting as well as you can. Margin loss. Here's another loss function that people are looking at. So you perform beam search until your correct hypothesis falls out of the beam. You restart the beam whenever there is a violation, and then you basically extract hypothesis and competing hypotheses. So here, for example, the idea is that if you have the correct output, a red dog runs quickly today, all of a sudden, this particular hypothesis falls out of your prediction, of your beam search, right? So if you're using a beam search of size 2, you will never get it right, because that's not going to be as the top 2 hypotheses. And so what you can do, you can construct this margin score. And this is a very useful construction to have. A lot of people are using it for multi-model learning, where you're trying to embed images and text. You're trying to bring them in the same space. And the margin loss is very simple. It's very easy to optimize. This is basically saying the following. Let's say I have score function for prediction of current output. Then I have a score function for predicting of the K best output. And I want to make sure, and you have some loss function, it's 0 when margin constraint is satisfied. So what you're effectively saying is you're effectively saying the following. If I look at my K best outputs using beam search, I want to make sure that my output of the model is among those K best. If it's among those K best, then my score is my loss is 0. If it's not, then I'm going to be penalizing myself by some margin. In this case, it's 1. Right? So this is very similar to the ranking loss. Right? So you're really trying to optimize for the settings where your prediction is at least larger than the kth best prediction by some margin. In this case, it's 1. And the margin itself is 1 because scaling here is irrelevant. You basically want to make sure that you are sitting among the k best predictions. And so for machine translation, these things work fairly well. Okay? So again, this is something if you're interested in the problem where you're really trying to optimize for the beam search. For the output, this is just appeared in 2016. And it's fairly easy to optimize. In the last part of the next, maybe 10 minutes, I wanted to look at the autoaggressive generative models. So there is one particular model called Pixel RNN, which is, I believe, it's currently state-of-the-art model for image generation. And it's, again, a version of sequence-to-sequence model. It's very frustrating that it's state-of-the-art, but it is. It's basically saying, you know what? It's a fully visible model. There are no hidden variables. It's similar to the language models with RNN, and you basically model pixels with softmax, which is crazy, because you're effectively saying that given this whole thing, I'm trying to predict the value of xi. And the value of xi is going to take a value between 1 and 256, right? And remember what the softmax is. The softmax has no notion of ordering. There is no notion that the pixel value of 253 and 254 somehow are related to each other, right? It's like independent predictions, right? And they have to sum up to 1. So people kind of knew about these ideas a long time ago, maybe 7, 8 years ago, but everybody thought this was crazy until people actually tried doing it on GPUs. So here's how you do. You first sample the first pixel from some prior distribution. You sample the second pixel from the 256-dimensional softmax, and so forth. And you keep sampling, right? And you keep sampling. And so now, for example, if I want to sample the next pixel, that's how my distribution would look like. So I sample from this distribution. If I sample from the next pixel, this is how my distribution might look like, right? This is a discrete distribution. This is a softmax distribution over 256 choices. And then I fill in the next one, and this is what it's going to look like, right? And I fill in the next one, this is what it's going to look like. So for example, here, we know that the value of the pixel here will be black, right? Just based on the overall context. And here we're basically saying, okay, what's the distribution of the next one? It's probably going to be close to white because we're trying to predict this value here, right? And so forth, right? And so all of a sudden you get this image, right? It's just an RNN predicting 1 pixel at a time. There are a few tricks that you can do. You can look at whenever you're trying to predict this pixel, you don't just look at the previous one, but you're actually looking at the neighborhoods, right? And so this is what samples from these models look like. Just treating sequence of pixels, much like predicting sequence of words. Yes?
Sorry, how are you doing the colors with this?
How do you do what?
How are you doing colors?
Oh, colors, yeah, it's 256 times 3.
Oh, but you're not like treating them as correlated in any way?
No.
Oh, wow.
So there is no like any correlations. You just have like 256, 256, 256. Or maybe what they've done is they basically, I think it's just they just stitch things together and that's it. Now each conditional probability, like if I go back here, each conditional probability here is like a crazy deep neural network. Right? It takes the whole overall context, it passes it through multiple layers, and then predicts, 256 numbers. I guess 256 times 3 numbers, right? And they've trained it on a lot of images. And so this was surprising in the sense that if you look at these images, like these look pretty good. I mean, not very coherent, but this was pretty surprising to a lot of people. Because before that, people were trying to generate, and generating images is really hard. You can also do interesting things like where these models shine up with occlusions. So if given half of the image, you generate the remaining ones, right? So you can see that sometimes it can generate like, looks like a dog, and sometimes generates some like something in the background and so forth, right? Like there's a bench in the background, or like a whole bunch of different things. And in terms of the quality, if I look at the log probability, these models do quite well. And this is what the original looks like. You can also do conditional pixel. In this case, it's convolutional neural nets. So you can do RNNs, or you can do convolutional nets. Just, you know, there's a few differences, but not that many. So you can like generate gray whales, and it generates. So the way you can think about conditioning is that conditioning is just another bias that comes into the model. So it's biasing the hidden states. That's all there is. There is nothing fancy about it. So here's another sort of application that this was done, I guess this was done by the same folks who did Pixel CNN. They kind of looked at the WaveNets, which is a generative model for raw audio. So they start at the input, right? And then using this hierarchy, kind of like a binary tree, they predict the next phoneme or the next piece of a sound, right? And so given the next piece of the sound, much like you've seen in Pixel RNN, you're just predicting the next sound. And again, taking the overall context, predicting the next sound. In context, predicting the next sound. It's just exactly the same model, but applied to a one-dimensional speech signal. By doing this kind of hierarchy here, you can see that what they've done is that the prediction for this time step can really take into account a huge context, right? Because, you know, it's almost like a logarithmic scale. So it can really take a large context into account to predict a single small representation. I mean, a single small speech signal. And they've had some successful results, because if you look at the speech, it actually is pretty good. The quality of the speech is pretty good. Let's see. No, it's crashed. Hold on a second. Every time I have a video, my PowerPoint crashes. Let's just let's see. Hopefully, it will not crash. Here's another example of, which also shows a video, of video pixel network. So you can go beyond it and you can say, fine, given the video, try to predict the next frame. Right? Exactly the same. There's been a lot of work coming out in terms of trying to predict. So here what you're doing is you're given some context, you're trying to predict where all the digits are going to be in the future, right? So you have to know something about the bouncing and what's the behavior of these digits. And there's been a lot of work. Some of my former students also were looking at this problem. It's kind of trying to predict what the future will look like given the past. Again, you can do sequence-to-sequence framework. Maybe just in the last few minutes, people have, you know, if you see what's been happening, a lot of work right now is people trying to come up with architectures. What are the right architectures to use? It's a very kind of search for the right architectures. Even though there have been a few papers where people are now doing like architecture search over GPUs, and burning a lot of GPUs to try different architectures for different problems. One thing that came up recently is this notion of self-attention. So in convolution, the way you do convolution is you kind of, you know, moving it like this. And people said, well, how about we do self-attention where everything is connected to everything, right? So you have some input, which is a sentence or a speech signal. And instead of doing convolution, you're looking at the bigger context effectively. Computationally, it's more expensive, but these systems tend to work way better for a lot of different tasks. And so there was also another paper called One Model to Learn Them All, which is basically, you have some encoder, different modalities, images, text, and such. You have a decoder, you're trying to predict something about images and text, and you have input-output mixer that picks up different modalities or does attention. Here's an example of paper where it basically says, well, your input could be an image, and it could output a caption, or your input could be an image, you output the category, or your input could be a language, and you can output a French sentence, or German, or your input could be an English sentence, and you can learn to parse. So you basically have one gigantic model that tries to do all of these tasks at the same time, right? And obviously there's some parameter sharing that happens. Different inputs would have their own different input representations, but it's almost, you can think of it as a multitask model. Depending on what the input is, you try to predict something else. The parameters of this model can be shared with the parameters of, you know, like when you're doing translation from French to English and so forth, right? So this is kind of an interesting idea where you have one gigantic model that tries to share a lot of different parameters between all of these different modalities and basically tries to solve these multiple tasks using a single model, right? Or using a single internal representation or internal state. So that's kind of interesting. Okay, on that note, I think I'm done. So next class, we're going to start looking at a class of, I believe we're going to start looking at the class of generative models. So we're going to look, so far we've looked at these video pixel, we've looked at pixel RNN and pixel CNNs, but we're going to start looking at, you know, more complex models that actually have some latent structure, some hidden representation. In some cases, these models will work better. In some cases, other models will work better. So we'll try to cover a whole spectrum of these models. So we're going to look at deep Bose machines. We're going to look at variational autoencoders, and later on, we're going to look at generative adversarial networks. Okay? Okay.